Okay. Thanks for coming, everyone. It's great to see everyone. So I'll be talking about an aspect of astronomy which I find very interesting, and I think it all starts with this plot over here, which shows you the variations in brightness of one particular star over time. The name of that star is Wolf-Rayet 140, as shown on the bottom. And so this is a compilation of data from many different years, and each different color corresponds to data from a different year. And so what seems to be happening is that all of a sudden the star got brighter by a factor of 10 before slowly declining again, and so becoming dimmer. And the whole process repeats itself once every 8 years. So ever since records began in 1977, it happened again in 1985, 1993, etc. So it seems to be a very periodic and predictable thing. So these observations were done in the infrared. And normally infrared flux in astronomy is associated with the production of dust, because dust particles emit in the infrared. And so the question here, what seems to be happening is that this star appears to be producing a whole bunch of dust once every 8 years before the dust fades away slowly and repeating itself again. So that requires an explanation. And the thing to know about this star is that Wolf-Rayet 140 is a type of Wolf-Rayet A star, which is a very, very massive star. So stars come in lots of different sizes. There's a sun, for example, which is a G star. It's not the smallest, but not huge. There's also stars like the O star, for example. Those ones are much larger. They start off at about 20 or 30 times the mass of the sun before as they evolve, they lose some mass, but they continue to be a very massive star. And these most massive stars terminate their evolution in a supernova explosion. And Wolf-Rayet stars corresponds to the final phase of evolution just before this O star explodes in a supernova. And so they're in a very unstable and sort of violent phase of evolution. They're about 1 million times brighter than the sun, and as a result of that luminosity, it's driving material outwards away from the star at about 1% the speed of light. So you can think of it as a star that's like so bright that's like blowing itself apart. And that just makes the question even worse, because once you produce dust, how can you have dust survive in such high temperatures and with such harsh UV ultraviolet radiation? And so that's all very mysterious. And what I haven't told you so far is that Wolf-Rayet 140 is actually not one star, but two stars. And the two stars go around each other in some kind of a very elliptical orbit. So this is called a binary, so two stars going around each other. And the period of this binary is exactly 8 years. So every 8 years they get very close to each other before they move far apart again. And the point of closest approach of the orbit appears to coincide with when the sudden brightening happens once every 8 years. So the natural question is that could the orbit of the binary have anything to do with the dust production mechanism? And so one theory is that what could be happening is that when the two stars get close enough to each other, because they're both really massive stars with very strong stellar winds, they could be close enough such that the stellar winds actually collide and form a very violent shock front. And at this kind of shock front, you could get a high enough density and the right temperatures to actually form dust. And so you can essentially think of this as a material being smashed into dust by the very fast speeds of stellar winds. And this only happens when the two stars are close enough, not when they're too far away. So that's why it only happens once every 8 years and not other times during the orbit. So it would be nice to actually see the dust coming out of that. For example, what shape is it, or is it even there in the first place? So we go to some of the biggest telescopes in the world. So these are the Keck telescopes in Hawaii. So it's on this summit called Mauna Kea. The summit is about 4,000 meters altitude, so you're above a lot of the moisture and a lot of the clouds. So you get very good observing conditions. And here's what we see when we zoom in really close to one system of this type. So this is Wolf-Rayet 104. It's not Wolf-Rayet 140, confusingly named, but it's a similar system. And the whole scale of one of these images, it's about the same angular size as if you hold like a pea 10 kilometers away. So it's very tiny on the sky. But with those very large telescopes, we could achieve that. So the telescopes are about 10 meters in diameter, which is among the biggest in the world. And so if you take a video of what's happening to the dust, it's not just a spiral, it's a spiral that's actually rotating. You can see it move in time. It's not moving as fast as shown here, this is a time lapse. But if you take an image once every few months, once every year or so, then you see this happening. And so that's very interesting. So the dust seems to be coming out in the shape of a spiral. And why is it? Well, spirals are quite common in nature, right? We see them in several places all the time, like snail shells, for example, or galaxies and planets. So very, very simple rules in nature seem to give rise to spirals. So what could be happening here? Well, it's exactly the same mechanism that I talked about. So when the stars are close enough, they collide. And because one star will have a slightly stronger solar wind, it pushes the entire shock front towards the other star. So it becomes like a cone at the large scale. And it's on the surface of the cone that you have the right conditions for dust to nucleate. And the simulation in the middle, so this bluish looking animation is showing you this process in action. It's actually identical to what's happening in a garden sprinkler. So every drop of water is coming in a straight line away from the garden sprinkler, but because the sprinkler itself is rotating, the whole trajectory of the water appears to be wrapped into a spiral. So Wolf 104 is quite unique. There are several other systems that were also discovered as part of the same campaign using the same telescope. So there's Wolf 98A. It has a spiral as well, and several other systems. So it seems like we found a whole class of systems making dust that come out in the shape of a spiral. And at the same time that there was this campaign to look at very close-in dust that's very tiny and very hot, there was also an attempt to image dust structures that's much further away. So does the close-in spiral go further out? So does it keep on spiraling out? And to do that is a bit more difficult because the dust gets to much cooler temperatures away from the star, and you can't see them as easily. But if you go to longer wavelengths, so in this case, the mid-infrared, then you could actually see that cooler dust. So here's an example of one of those systems being imaged. So this is dust that's much further away from the star, and now you can see many periods of spirals. So not just one or half a spiral. You see the whole thing go around many times. But it also looks a little bit weird because you can see the edges are a bit squarish. So how do you explain that? So to do that, it's the same model, but we need something that's slightly more three-dimensional and complete. So what's really being wrapped into a spiral isn't just a straight line of dust. As I was saying, dust forms on a conical shock front. So you're really wrapping a whole cone into a spiral, and it's on the surface of that cone that you have dust. And so you can specify the geometry of that cone using some very simple intuitive parameters like how the binary orbits each other, how fast the whole thing is expanding, for example, and also how thick the cone is, or what's the opening angle of that cone. And if you do that to Wolf 112, that's what you get. So in the middle, that animation shows you the assembly of essentially a cone wrapped into a spiral. And if you view the same thing from the edge-on perspective, so you tilt it around, look at it from the side, then you get the thing on the left. So that's what gives rise to that squarish pattern. And on the very right-hand side, that panel shows you how the system would evolve in time. So the binary comes in and out of the orbital plane, or in and out of this page, and as a result, you get, in the projected sky plane, the dust looking like ripples rippling up and down. And so we can try and compare that to the observations. Let me find my mouse. So on the left is the model, on the right is the observations over many years, and you can see they match each other quite well. So yeah, so I think we have a decent understanding of what's happening in this system. So here's another very interesting one. So if you look, so this is called APEP, the star's called APEP. If you look in the infrared, you don't see anything except for stars. If you look at the mid-infrared, where you see cooler dust, then you see this huge, very big spiral structure that's really beautiful and intricately detailed. And so how do we explain this? So we don't see images like this every day in astronomy. If you see something like that, that's you would want to explain all the details in there. So is this also a colliding wind binary? Well, yes, it is. So in this case, we could actually image very close in to where the whole action happens. So I think this was using a series of telescopes in the radio wavelengths across Australia, all working at the same time. So you get extremely high resolutions. And you can see at the very core of the entire spiral is the shock front. So this is where the wind shock happens. That's where the material coming from the two stars actually collide and give off emission at the location where they collide. And that's essentially the apex of the entire cone that's being wrapped up into this spiral. And you can't see the two stars directly because they're too close. But if you use a very specialized aperture, and you look at the interference pattern of the two stars through that aperture, you can infer the positions and orientations and everything to do with the two stars. So if you do that, and you can see that the orientation and location of the two stars are very consistent with that shock front. So I think we have a pretty good understanding as well of the central engine. And so what's left is how do we link together this very close-in scenario to what we see on the very outside, so the cool dust with this huge intricately shaped spiral. And well, it's actually the same thing. So again, we have on the left a whole cone wrapped up into a spiral. The only trick here that's different is that apex seems to be a very elliptical orbit. So the two stars go around each other in a highly elliptical orbit. Sometimes they're very close to each other, other times they're really far away. And that results in some kind of distortion to the spiral, giving you this shape. Another thing to note is that precisely because that the distance between the two stars change, they're not always close enough for the winds to collide. You also don't produce dust when the two stars are too far. So you have to chop off the bit of dust that would have been produced if the star was too far away. So that's on the right, you see the chopping off of the dust that don't actually exist. And you get a pretty good model. So again, it's the same thing. It's a cone wrapped up into a spiral that gives you this projected image. There's all the same mechanism. So just to recap, we've seen a few different structures so far. These nice, very simple spirals and slightly squarish spirals, and this really big and well, kind of fat-looking spiral. And they're all the same thing. They all come from the same underlying physical mechanism. So let's go back to Wolf-Rayet 140 for a moment. So that's where we started. And so this is the star that was getting brighter once every 8 years, very suddenly, and then dimming again. So this is the dust that's being produced. That's what it looks like. And starting from the top left panel, we can see the whole thing expand and eventually become the two really large structures on the right. So don't worry about the thing at the center. That's the star. So the star is very bright and it diffracts through the pupil of the telescope, giving you this very complicated diffraction pattern. So that's just the star, but everything else on the outside is the dust. So you can see the whole thing expand, but presumably it'll be easy to make a model, right? Since we can already model all those very complicated structures. But I think every time you try and do something you think is very simple, I think often nature teaches you something new. And so in this case, what we realize is that not only do you not produce dust when you're too far away, you also don't seem to have the right conditions when the two stars are too close to each other. So if you produce dust as long as you think they're close enough, then you get, so of the panel of four, you get the two on the left, which has a whole bunch of structures such as sorry, I can't find my cursor, but to the north, you don't see that in the data. So there's a whole bunch of structures missing that corresponds to dust that would have been produced if the two stars are very close. And so there seems to be like a Goldilocks zone of dust production. You need conditions to be just right, so you get the right density at this conical shock front for dust to precipitate. And if you play the model in time, you get the animation on the left, and at different points in time, it matches the observations on the right. But actually, that's not the whole story, because when you put all these images next to each other and you actually try and figure out how fast this whole thing is expanding, it appears to be getting faster and faster. And so why could that be the case? So previously we thought that all of these systems that make spirally dust, the spiral just sort of coasts out at some very high speed into the void. But they shouldn't be picking up more speed. Why is it getting faster and faster in this case as it expands? So I put an image of the sun here just to remind you that stars give off a lot of light. So in this case, the amount of acceleration experienced by the dust is equal to what you expect from light. So light is made up of photons. Photons carry momentum, and this momentum gets caught by the dust that's surrounding the star, and it harvests that momentum and it picks up speed. And so, quite simply, it's a bit like a light sail, it's like a solar sail. It's capturing the momentum coming from the light at the very inside where the star is. And I think that's very interesting because it's not uncommon to see things moving around space at very high speeds. But it's very hard to see acceleration that's due to anything that's not gravity. We know that light plays a very important role in lots of different settings, such as how the way we form planets, the way material or dust gets removed from planetary systems, but it's very hard to see these things either because they're too small or too faint, or the whole process happens too quickly, so it very quickly equilibrates or balances out with some other force. But this appears to be a system in which the star is so bright that even at these scales we can actually catch on camera the whole dust structure expanding at an accelerated rate. So I think that's very interesting. So an example in astronomy, perhaps the first one, the first direct witness of light dynamically interacting with matter. So some of you may have heard of the James Webb Space Telescope, which is like the new big thing in astronomy. You may know the Hubble Space Telescope. It was the previous big thing in astronomy, but that's the new thing now. That's the new favorite toy of astronomers. And a year ago, it was launched from Earth, and it's put on this orbit near what's called the L2 Lagrange points, which is where the gravity of the Earth and the Sun and the whole orbital motion all sort of somehow balance each other out. And you get a region with a relatively flat potential. But anyway, so the telescope's rule is there somewhere really far away. And we thought, oh, would it be nice to look at this with the Webb telescope all the way out there in space. So this is the image that we saw earlier from Hawaii. This is a ground-based telescope. And this is what James Webb saw. So it sees not just one ring or one period of shell, it sees three of those, but actually not just three of those, because if we dramatically zoom out of this image, then what we see is 20 concentric dust shells all nested inside of each other, which is really remarkable. You don't see these images every day in astronomy of single objects. I think what's really remarkable is the whole thing's about 2 light years across. So this is really, really huge. The temperature is quite cool. We can see it because we have very high sensitivity on the telescope out there in space at very low temperatures and no atmosphere. And so essentially, if you shoot a beam of light from the bottom right-hand corner, it takes 2 years for it to travel to the other side. So yeah, that's how big the structure is in reality. And so the thing with James Webb is that everything, well, and things in astronomy in general, is that all this data gets published or becomes publicly available essentially in real time as it's being taken. So it very quickly made its way to Reddit and then to more mainstream news. So you get these very funny headlines like rectangle-shaped rings in space and perplexing astronomers, etc. So apparently everyone's very confused about what's actually happening. And but I think we all know what gives rise to this structure by now. So this is the original model of just one ring. It's the same structure that's part of a cone, wrapped up, but you chop off the bits that correspond to where no dust is produced. So essentially 2 rings that are at different orientations in space. And if you stack 3 of those on top of each other, you get that. And if you do 5, you get this. And if you just simply stack 20 of those all on top of each other, then you get pretty much exactly what we see in the observation. So yes, we do actually know what's happening. And I think what's really interesting is that, so don't worry about the blue sparks. Those are artifacts from the telescope. But this diagonal yellowish, really bright line is actually a real feature that's predicted by the model. So simply by stacking a lot of features on top of each other, the very central bit that's running through gets enhanced by such an extent that it becomes like a very bright needle. Anyway, just fun fact. So if you look at the same system from the phase-length perspective, then you don't get the weird rectangular rings, you get the normal circular rings. But I was saying only the right parts of the orbit corresponds to dust being produced, so it doesn't span the entire revolution, only parts of the circle. So we published that and it's debunked. There's all these speculations about aliens and alien megastructures. Yes, so don't trust everything you read in astronomy, and indeed anything. So I'll conclude by saying that so the process that we study these systems from 1977 or so, well, we, not me, but people, is like it's a bit like looking at a train. In the beginning, you see this whole bunch of dust and smoke coming out. You don't really know what's happening, but as we get better instruments, we can start to think of why that happens. We can see exactly what's the shape of that dust. And in some cases, we can actually go all the way into the engine and see exactly where the 2 stars are, how they collide, and how the dust is formed. And eventually, everything comes together through some model, or they all come together, and you think you have a good understanding. But I think there's a lot more we like to learn about these systems. And with new telescopes like the Webb telescope, and also new upcoming instruments, there'll be a lot more that we'll learn. Especially about the dynamical processes and chemical interactions as well. So I'll leave the images up here and be happy to take any questions if you want.
Brace yourself for lights. Do we have any questions from a speaker? Yes.
So, nice talking. The dust you're talking about, what chemical elements are in that?
So the main thing about this dust is it's carbonaceous dust. It could have, well, it depends on the particular system, but essentially whatever is contained in the cell wind can become part of the dust. So the thing about Wolf-Rayet stars that's different from normal stars give out mostly hydrogen, but Wolf-Rayet stars have depleted that hydrogen. So the dust coming out is normally much heavier. Depending on the type, it could be very heavy in carbon or sometimes oxygen and nitrogen. So in these systems that make dust, it's primarily the very carbonaceous Wolf-Rayet stars. So carbon is the main ingredient in the dust. But you also get silicate features and other things as well. But I'll say carbon is the main thing to know about these dusts.
Are the Wolf-Rayet stars in the main sequence, or are they almost like dwarfs?
Yeah, Wolf-Rayet stars are way off the main sequence. So the bigger the star is, the faster it evolves. And Wolf-Rayet stars are off the main sequence and just about to explode. So O stars evolve for about 10 million years or so, or maybe even less than that. And the amount of time it spends on the main sequence is maybe around half of that. And so the entire Wolf-Rayet phase is the final 10 or 20 maybe 10% or so. So it spends about 1 million years on the Wolf-Rayet phase and the whole thing explodes. So it's not in the main sequence.
If a winter Wolf-Rayet star turned red or normal colour,
So you're talking about the apparent.
when it's gone off the main sequence, does it turn redder?
So they do turn redder, but the primary reason they turn redder is because they make dust. So the dust in these cases will enshroud the entire photosphere, and in some cases you almost can't see the photosphere at some wavelengths. So the reddening, a lot of it is just because of the fact that it makes dust.
Not in the same way as bits or goose.
Oh no, that's different. Yeah.
Aren't there the Wolf-Rayet stars extreme blue?
Well, if they're a Wolf-Rayet star, then they're off the main sequence. Then no, I don't think so.
Why don't we kind of break this conversation off during tea time, perhaps? Do we have any other questions? So,
Are these stars very common or are they rare?
They're really rare. They're very rare. So I think about 1 in a billion or 1 in 100 million stars in a galaxy are Wolf-Rayet stars, around about that. And so in the entire galaxy, there's only the order of a few hundred to maybe 1,000 or so of these stars. So they're quite rare. And the ones that are in binaries are even less than that. The ones that are in the right binaries to make dust is even fewer than that. And so pretty much all the images you saw are all the good images we have of all of these systems that make dust. So the ones that do make dust that's imageable is very rare. Get a handful or so in the entire galaxy that we know of.
How do they actually give off the dust?
Yeah, that's a good question. So so we talked a lot about how the dust forms. The reason that the dust moves away is because they form on the shock front, and the shock front is not stationary. It's forming at an angle. So if you've got two stars here, then you have this shock front. Then the wind speed is actually going these two directions, and this speed is approximately equal to the wind speed of the stars coming out. It's just the way that the winds interact. So it just drifts as a result of the momentum interaction on that surface. That's the reason it moves away. And it could pick up more speed if the star here is really bright. That could give more speed as a result of radiation pressure from the light. That's what we're talking about.
and question at the back.
Yeah. So there's no correlation. That needle isn't actually going through the star. It's the results of projection effects because you're looking at just the right angle, and all the dust stacks up, and it looks as though it's a needle. It's not actually a real needle in three-dimensional space. No. So yeah, I think I get what you were describing. So, but the needle doesn't actually exist in 3D. So if you were to go there in person, you don't see that needle there. The needle is only there because you have a ring that's viewed edge on, and it happens to coincide with what looks like a needle. So there's actually no real needle. But there are stars that give off jets. But this is not an example of those.
Again, I think the question is like, do you get dust preferentially coming out of the north and south
Oh.
like the jets, and that's what's kind of causing the projection effects?
Oh,
Because you get dust preferentially ejected from the poles like a jet.
yeah. You don't actually get dust preference. So dust doesn't come out of the star. So the star only gives out gas-like material in stellar winds. It's when the stellar winds collide that you get dust, which is why you only get dust that form on this surface. And for this part of the orbit, you form dust in the form of a ring, but you get all these rings stacked up together. Then this starts to look like a needle. So the needle is really a bunch of rings stacked together. The star itself doesn't give off the dust.
Wonderful. Okay, so I think it's time for a tea break, after which we'll be learning about astronomy and the eye from Brian at CAA. Before that, we back to our speaker again. There's a chance you might get some questions. Do you want a cup of